Hi there, Mr. Sutton here with the AB Calculus 615 classwork solutions on integration with respect to y. For this problem, we're being asked to find the area of the region enclosed by these curves here. Let's start by graphing it out. So I've entered f and g in my y equals as y1 and y2. Not really sure what window I should use on this one, so I'm just going to do a zoom 6, zoom standard. So there's my square root, here's my line, and I've got this bounded region in here now that I'm trying to find the area of. Now, if I try to do this with respect to x, using vertical distance strips, I'm going to have two bottom functions. We start off with the y-axis, but then it kind of shifts to this line instead. So that's going to take two integrals. If I do this with respect to y going horizontally instead, then I only need to use one integral. So I'm going to use y integration on this one. So I'm just going to convert all of these to functions of y now. This first one, I can turn this into x equals y squared, or f of y equals y squared. For this next one, I'm going to, add 1 to the other side and multiply by 2. So I'm going to have y plus 1 quantity multiplied by 2. That's what g of y is going to equal. And I still, of course, have my horizontal line at y equals 0. So now to get the area here, I also need to get the limits of integration. So we're starting at a y value of 0 because that's where this horizontal line is leaving us. But what about this top spot here? I need to find the intersection point up here. So for that, I'm going to go back to the calculator. And let's see here. I'm going to do second trace and then option 5 for intersect. And let's move my little spider over to this intersection point. Enter 3 times. 1, 2, 3. And let's see here. Normally I would look at the x value, but now I care about the y value because it's a y integration. So I have a y value of about 2.7321. So f of y equals g of y at, and I'm going to actually give this point a name. I'm going to call this p. So y equals p equals 2.7321. And I'm also going to store that on the calculator. So to store this on the calculator, this is a little bit tricky. It's a little different than what we normally do. I'm going to quit out of here, and instead of just pressing store, which would automatically store the x value of the intersection, I want to store the y value. So I have to do alpha and then y, and then I have to store that. And I'm going to store that as, let me do alpha p. So when you get an intersection on the calculator, your calculator automatically stores the x value in x and the y value in y, but y values get overwritten all the time. So this is why I'm storing this as a different constant instead of just using y. All right, so at this point then, I need the integral from, we'll call this 0 to p of the following. So I need to do right minus left if I'm integrating horizontally here. So that would be, let's see here, g of y is the rightmost function, f of y is the one on the left. So this is going to be g of y minus f of y dy. And now it's back to the calculator for this. So here's what this looks like when I do it on the calculator. I've got the integral from 0 to p, and then instead of using y in my integral, I'm just going to use x's, and as long as I do that all the way across, then my calculator will figure out what this actually is numerically. So we've got 2 times, this is really y plus 1 minus y squared dy, giving me 6.131. For this problem, I'm trying to find the volume if I revolve this bounded region around the y-axis. So let me start by graphing this out. To do this, in my calculator, I'm going to enter 1 minus x squared in my y equals, and this is not the same function as this one, but I'm going to use this kind of setup to actually sketch what this looks like. So let me deselect that function since it's not the actual one I want to graph. And then let me escape here. And now I'm going to do second program, which brings up the draw menu. Option 8 gives me draw inverse. And now I'm going to put alpha trace y1 in here. So when you do draw inverse on 1 minus x squared, your calculator actually is going to try to graph 1 minus y squared, because that's just the way this works. It uses y instead of x. So there's 1 minus y squared, and it's this sideways parabola, which is awesome. So we're basically trying to revolve this little region up here. It's between the function here it's between the y-axis, and it's in the first quadrant. And this is going around the y-axis. Because the y-axis, the axis of revolution, is one of the boundaries for this bounded region, that means that we can use pancakes, or disks if we're being technical. So our area formula for our cross sections is going to be a of y equals pi r squared. The radius is just going to be the distance between the y-axis and this function, and it's an x value kind of radius. Fortunately, our function is already in terms of y right here, with x as an output. So I can just write in pi times 1 minus y squared. And now I'm going to do this on the calculator. So I'm going to have the integral from y equals 0 to y equals 1 of, and then just this a of y dy, which I'll now put in my calculator. Now, on my calculator, I already have this expression, 1 minus something squared, in my y equals. So I'm just going to do, let's see, I'm going to go to my y equals again, and I'm going to put the area formula in as y2. I like doing all of this in the y equals. So this is going to be pi times this stuff I'm just going to represent as alpha trace y1. It's 1 minus something squared. And then I'm actually squaring that whole function there. So let me square this. Let me quit out now, and I'll go to Math 9 for my integral. We're going from 0 to 1. Alpha trace y2 now, because that's where I have my area. And then I'll just do dx for that. And that comes out to about 1.676. For this problem, we want to take the area between x squared and 2x and revolve that around the y-axis. Let me start by graphing this. So putting those in my y1 and my y2, I'm going to do a zoom 6 because I have no idea where these actually intersect. All right, I could probably zoom in a little bit here. So let's see here. This is going to be between essentially 0 and, I don't know, roughly 3 or 4. Let's do 3. And zoom fit just to get a closer look at that. There's my parabola. There's my line. Beautiful. So I'm taking this area here and going around the y-axis, like so. Because I'm integrating horizontally here around a vertical line, this means I'm going to need to have functions of y rather than functions of x. So let me take a moment to rewrite these. This first one, if I think of f of x as y, I can square root both sides, and I can say x equals square root of y, or f of y equals radical y. For this other one, I'm just going to divide by 2, so I can write f of y equals y over 2. And now I've got these expressed in terms of y. I'm also going to have to get an area formula out of this. But real quick before I do that, let me actually take a moment to find my limits of integration. So I need my lower y value and my upper y value. Now, I could solve this algebraically by literally setting these two things equal to each other, but I've already got this thing graphed out, so let me just go back to my graph. I mean, clearly we're crossing at the origin, but what's this other intersection point? It kind of looks like 4, but just to be on the safe side, I'm going to do alpha trace, or rather second trace, intersect, option 5, move my spider over there, enter, 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 and yes, indeed, we have a y value of 4 right there. So these two functions of y equal each other at 0 and y, so those are going to be our limits of integration in a moment. And now I have to get my actual area of my cross-section. I'm going to have to use washers here because I've got a space between my bounded region and the axis of revolution, the y-axis. So I've got, in general, a of y equals pi times big R squared minus little r squared. Big R, that's going to be the distance between the y-axis and this further away function for my bounded region. So that's going to be, let's see here, this further away one, this is the square root of y. So this is going to be square root of y then for big R squared. And then, let's see, so I'll just write that as f of y in there. And then my little radius, that's going to be the distance between this closer part of my bounded region, g of y, and the y-axis. So that's just g of y minus 0, or just g of y, that I'm squaring in there. And now let me put all of this in the calculator and take the integral from 0 to 4 of, well, just this a of y dy that I just came up with. To make life a little bit easier, I'm actually going to put my area formula under y3 on my calculator. So I've got my pi, and then f of y squared, that's really the square root of y squared. And I'm going to enter everything in terms of x. My calculator can deal with it as long as I write dx down here. But this square root of y squared is really just y, so I'm just going to write x here. I'm not going to bother square rooting and squaring on the calculator. I'll probably make a mistake trying to do that. Now I'm going to do 1/2 x, which is really 1/2 y, and I'm squaring that as well. Let me quit out of there now, and I'll do math 9, integral from 0 to 4. And now I stored that. Where did I store that? Was it y1 or y2 or y3? I stored that in y3. So let me do alpha trace y3 and then dx, and that comes out to 8.378. For this no calculator problem, we're taking the region enclosed by the y-axis, the line y equals 2, and the curve y equals square root of x. So if you graph all this out without a calculator, it's kind of giving you a curved sort of triangular area. We want to revolve that around the y-axis. All right, so I'm going to start by expressing this in terms of y, since I'm going horizontally around a vertical line. So I'm going to rewrite this as x equals y squared. And then the area of my cross sections, since this whole area between the y-axis, a horizontal line, and the function is flush against the y-axis, I'm going to use discs on this one. So I'm going to write a of y equals pi r squared instead of the washer formula. So for my radius, that's just going to be the distance from the y-axis to this function here, this y squared. So that's just going to be pi times y squared squared. Since I have to do this by hand without a calculator, let me simplify that a little bit more. So this is pi times y to the 4th. And in terms of my limits of integration, I'm going from the origin to up to y equals 2, where this intersects the square root function. So this is going to be from, let's see, 0 to 2 for the volume. And we're integrating this formula here, pi times y to the 4th, dy. Now I'm going to take my antiderivative. This bumps up to an exponent of 5. So that's pi over 5 y to the 5th, evaluated from 0 to 2. So that's all this stuff with 2 plugged in. And I'll take a pi over 5 out of here now. So we'll have 2 to the 5th rather inside, minus 0 to the 5th. 0 to the 5th is obviously just 0. So we have pi over 5 times 32, which is 32 pi over 5. And that gives us answer choice A. For this problem, they're telling us the base of a solid is the region in the first quadrant enclosed by this upside-down parabola and the coordinate axes. Cross-sections perpendicular to the y-axis are squares. We want the volume. So this is a calculator question. I mean, you can look at the answer choices and tell you're not really going to need the calculator on this one, but you can use it if you wanted to graph this. Whether you do it by hand or by calculator, you have this upside-down parabola going through the y-axis at 2 here. And now we need to get the volume of the cross-sections if we take this little region here and take squares coming out of that with squares perpendicular to the y-axis. All right, so let's start by expressing this function in terms of y. Because if you're going around the y-axis, you need y integration. So I'll start up here by subtracting 2. That's going to be y minus 2. Negating all of that to get a positive x squared. That's going to give us 2 minus y. And then square rooting, we have the square root of 2 minus y that x equals. Now to get my area formula, so my square cross-section is going to have an area of s squared in general. S, the base of the squares, since they're being perpendicular to the y-axis, it's just the distance from the y-axis to this function, which you just defined in terms of y up here. So this is just going to be the square root of 2 minus y squared, which I can just cancel out the square and the square root and call this 2 minus y. Normally I wouldn't bother, but looking at my answer choices, I'm going to need this simplified because I'm going to put this in my integral in just a moment. Now, right away, you can already see that since this is my area and this is the thing I need to integrate, there's only one answer choice that has that, choice B. But let's keep going just to make sure. So now let me get my limits of integration. We're going from y equals 0 to, it looks like y equals 2. If you're really unsure, you could set this equal to 0 for the x value, square both sides and add y to get y equals 2. So we're going to have the integral then from 0 to 2 of this area function here, 2 minus y dy, and that is going to end up giving you answer choice B. For this free response problem, which is calculator based, we want this R region in the first quadrant bounded by the x-axis, and this is, let's see, ln of x and 5 minus x. We want to take this region and find the area for the first part of this problem. All right, so I'm going to start this whole thing by renaming these functions. I'm going to call ln of x f of x, and I'll call this 5 minus x g of x, just so I can quickly refer to them. If I want the area here, there's a few ways I could do this. I could do it with respect to y and just have one integral, but then I'm going to have to rewrite these in terms of y. Or I can split this up into two integrals and just keep these in terms of x. Since I've already got these in terms of x, let me just use two integrals. To do this, I'm going to need to define what this intersection point is. So let me go on my calculator now and figure out where f of x and g of x equal each other. So I've got these entered in my y equals, and this is actually one of the rare times where you have some idea what interval you need to graph it in, because it looks like I'm going from 0 to 5 on their graph. So let me just kind of mimic that in my window. Let me do 0 to 5, zoom fit, and here's my ln function, which they didn't bother showing below the axis there. We've got this intersection right here. Let me do second trace, option 5, and then enter, enter, enter near that intersection, 1, 2, 3. Gives me an x value of about 3.6934. And on paper, I'm going to call that p, so I don't have to keep writing it. I'm also going to quit out of my graph, and I'm going to store that value as alpha p on the calculator. So now I can use it whenever I want. All right, so to get the area then, I'm going to need two integrals. I'm going to need the integral from 1 to p of, we're doing top minus bottom, so that would be f of x dx, so f of x minus 0. And then I need to add to that the integral from p to 5 of, well, this is now going to be the g of x function. Going back to my calculator and doing that out, I've got my integral from 1 to p of, this is f of x right here, and I'm adding the integral from p to 5 of g of x dx for everything. That comes out to about 2.986. For this next problem, they're telling us this region R is the base of a solid, and each cross-section perpendicular to the x-axis is a square. Write but don't evaluate an expression with integrals that gives you the volume of the solid. And this is one of the reasons I didn't bother integrating with respect to y on the first problem, because they're telling us here each cross-section is perpendicular to the x-axis. So for this one, I'm going to need to integrate left to right anyway rather than bottom to top. So for this, I'm going to need that p-value that I already found, this x value where these functions intersect. That's the cutoff from one integral to the other. So let me just write this out now. My cross-sections, they tell us, are squares. So I can write a of x equals s squared. And the square, the base here, this is just this length here, putting these squares in here. So this is going to be from 1 to p, this s squared is really going to be the f function squared. And from p to 5, this is going to be the g function squared. I'm just writing out some integrals now. I can write that this, my volume is going to equal the integral from 1 to p of f of x squared. That's s squared from 1 to p. And we have a dx there. Plus the integral from p to 5 of, well, now I need to square g of x. And they just said write out but don't evaluate, so this is done. For this last problem part, they're telling us the horizontal line, y equals k, divides R into two regions of equal area. They want an equation with integrals that gives us the value of k. But the good thing is we don't have to actually solve it. So I'm just going to get a visual here. I'm going to draw a horizontal line somewhere in there. And yeah, this probably isn't two equal areas, but whatever. This is the idea. we need to set up an integral involving k that basically sets these two areas equal to each other. So let's see if we can express the area at least of one of these, and then we'll get the other one as well. To get my area, the way that this is drawn out, it's probably going to be easier if I think about this in terms of right minus left instead of top minus bottom. If I tried doing integrals integrating vertically from left to right here, I'm going to have one top function. That's going to switch to the line y equals k. Then I've got another top function. That's going to be like 3 integrals to get one of these areas, which is going to be kind of annoying. Versus, I mean, up here even it's 2 different top functions. So rather than trying to think about this with respect to x, let me do this with respect to y. It's just going to save a whole lot of time. But to do that, I have to rewrite these functions as functions of y. So for this first one here, I'm just going to raise e to both sides, and I can write x equals e to the y, or f of y equals e to the y. For this other one, I'm just going to subtract y and add x to the other side. So this is going to be g of y equals 5 minus y. And the only other thing I'm going to need here is to figure out the y value where these two functions intersect. So let me go back to my grapher. Because I already have these two things graphed out, let me do second, trace, and intersect again. And this time I'm going to pay a little more attention to the y value at this point of intersection. So 1, 2, 3 button presses. And the y value there is about 1.3066 if I round that off. So I'm going to say these functions equal each other at this y value, which I'm going to call q on my paper here so I don't have to keep rewriting it. Now I would normally store this in my calculator as well, but since I don't actually have to solve this equation, I'm not going to bother because I'm not going to be using the calculator for the rest of this problem. All right, so I'm going to have an integral then for the area of this bottom part. I'm going to have an integral from 0 to k, because that's the y value up here, of, we have to do right minus left. So this is going to be g of y minus f of y dy. So this integral gives us the area of this bottom half. And now I need to set that equal to the area of the top half here. So that integral representing this area, we're going to be having an integral from k to q, the y value q. And that's also going to be g of y minus f of y. It's still right minus left, and the right and left haven't changed, just the limits of integration. So this is an equation that I can use to solve for k, and they just wanted me to set this up, so at this point I'm done.